Hello everyone, in today's lecture we are going to study next method of finding the particular integral which is known as shortcut method. So depending upon the right hand side function in the given non-homogeneous differential equation, we are going to consider different cases in this shortcut method. So let us see first case out of those 5 cases. Suppose the given differential equation is phi of d of y is equal to f of x, and this f of x is the function e raised to ax, where a is any constant. Hence the given differential equation it becomes phi of d of y is equal to e raised to ax. Now we want to obtain particular integral to this given differential equation. We know its formula. It is given by yp is equal to 1 upon phi of d of e raised to ax. To get this particular integral, now again we will go back to the given differential equation. We replace this phi of d by its expression, and therefore this equation it becomes d raised to n plus a1 d raised to n minus 1 plus so on plus an minus 1 d plus an into y is equal to e raised to x. Now what we are going to do? We are going to evaluate all the terms from the expression of phi of d. So let us see that. So derivative of e raised to x is equal to a into e raised to x. Now evaluate second order derivative. So d square of e raised to x is equal to a square into e raised to x. Similarly, the nth order derivative will be d raised to n of e raised to x is equal to a raised to n into e raised to x. Replace all these values in phi of d. So that will gives us d raised to n plus a1 d raised to n minus 1 plus so on plus an minus 1 d plus an of e raised to ax, because each term is containing e raised to ax function, is equal to, now replace all these terms by their corresponding values, which will gives us a raised to n plus a1 into a raised to n minus 1 plus a2 into a raised to n minus 2 plus so on plus an minus 1 into a plus an into e raised to ax. But what is this? This is the polynomial phi of d, and we can clearly observe that each d here it is replaced by a. So if we compare both the sides, left and right hand side, so we will be easily writing this thing that phi of d of e raised to x is equal to phi of a into e raised to x. So from above expression we got this expression. Our aim is to find 1 upon phi of d of e raised to x. For that purpose, now we will operate the operator 1 upon phi of d on both the sides, and we will be getting the expression as 1 upon phi of d of e raised to x is equal to 1 upon phi of d of phi of a into e raised to x. We will simplify it further. It will give us phi of d will get cancelled. We left with e raised to x on the left hand side equal to, as phi of a is constant, we have taken it outside of the operator and we left with 1 upon phi of d into e raised to x. We want 1 upon phi of d of e raised to x. For that reason, we will divide on both the sides by phi of a, which gives us 1 upon phi of a of e raised to x is equal to 1 upon phi of d of e raised to x. But this is possible only when this phi of a is non-zero. Now, we rewrite this expression as 1 upon phi of d of e raised to x is equal to 1 upon phi of a into e raised to x. Now see, which is the required term. This is the particular integral for which we got the expression as 1 upon phi of a into e raised to x. So comparing both the sides, what we understood from this? To get the particular integral in case of the function e raised to x, simply we have to replace this d by the coefficient of x, which is a here, in the exponential function. That will give us 1 upon phi of a into e raised to x. But provided, what is the condition? This denominator, it must not be 0. That is, provided phi of a is not equal to 0. Then what happen if this phi of a is equal to 0? So we'll consider that case. Then this a, as phi of a is equal to 0, this a will be the root of the auxiliary equation phi of d equal to 0, and hence we can able to write this phi of d as phi of d is equal to d minus a into psi of d is equal to 0. So this d minus a is the factor corresponding to the root a. Now we will replace phi of d by this expression in the above case. That will give us 1 upon phi of d of e raised to ax is equal to 1 upon d minus a into psi of d of e raised to ax. Now this psi of d, uh, as a is the root of the auxiliary equation phi of d equal to 0. So we have separated out that factor d minus a. Therefore, obviously this psi of d will not be 0 now if we replace d by a, and therefore using the first case we can write this expression as 1 upon d minus a into psi of a of e raised to x. So see, here we have replaced d by a. This psi of a is constant now. Now we will operate 1 upon d minus a on e raised to ax. So please recall here general method and operate this operator on the function e raised to ax, which will give us 1 upon psi of a of e raised to ax into e raised to x integration of e raised to minus ax, this function e raised to ax dx. Simplify the integrand. That will give us e raised to minus x plus x, that is e raised to 0, which is 1. Hence we get 1 upon psi of a into e raised to x integration 1 dx, whose integration is x. Now on the left hand side we are having our expression in terms of phi. So we will try to express our RHS also in terms of phi, for which we will again consider phi of d is equal to d minus a into psi of d. Differentiate this relation, which gives us phi dash of d is equal to, apply the product rule of derivative, using which we will be getting d minus a into psi dash of d plus psi of d into derivative of d minus a, which is 1. As we want psi of a here, so evaluate the value of this expression at a point d is equal to a. That will give us phi dash of a is equal to a minus a, which is 0. So this whole term it becomes 0 plus psi of a, and therefore above expression it becomes now 1 upon phi of d of e raised to ax is equal to x divided by phi dash of a into e raised to ax. Again, as phi dash of a is in denominator, there is again the condition that provided that this denominator phi dash of a should not be equal to 0. Now, if this phi dash of a is equal to 0, then what will happen? If it is 0, then again we will use the previous case, using which we will get 1 upon phi of d of e raised to x is equal to x square divided by phi double dash of a into e raised to ax, as phi double dash of a is in denominator, provided that it must not be 0. So that is the condition. Phi double dash of a not equal to 0. So from these cases, now we are going to write down few remarks. So see the remark. First, if our phi of d is of the type d minus a raised to n and the function is e raised to x, then using previous cases we will be getting it as x raised to n divided by n factorial into e raised to x. This is very straightforward now if you observe this term. Second, 1 upon d minus a raised to r into psi of d of e raised to x. If our phi of d is of this type, then what will be the particular integral? It is x raised to r divided by r factorial. This r is the power of linear factor d minus a, and this a in the linear factor and the coefficient of x in the exponential function, they must be same in both the cases. Then and only then we can use this remark. So which is x raised to r divided by r factorial into psi of a into e raised to x. Again, as the psi of a is in denominator, so provided that the psi of a should not be 0. Now we will consider the next exponential function. So if f of x is equal to a raised to x, which can be expressed into the exponential function e as e raised to x into log a. Therefore, particular integral will be 1 upon phi of d of a raised to x is equal to 1 upon phi of. Now we have to replace this d by the coefficient of x in the in the exponential function. In this case, here it is log of a. So we have replaced d by log a and we got particular integral as 1 upon phi of log a into a raised to x. Similarly, if f of x is equal to a raised to minus x, can be expressed into the exponential function e as x into minus of log a. And using first case, particular integral will be evaluated as 1 upon phi of d of a raised to minus x is equal to 1 upon phi of, replace this d by the coefficient of x into the exponential function, which is minus log a into a raised to minus x. And the last remark is, if f of x is equal to a, means if f of x is the constant function, then in that case how particular integral will be evaluated. So a can be expressed as a into e raised to 0x. So therefore, particular integral will be 1 upon phi of d of a is equal to 1 upon phi of. Now, in this case, coefficient of x in the exponential function is 0. So replace d by 0 and a is constant. So we will keep it as it is. So in this way, we will evaluate particular integral in case of the if our f of x is the constant function, provided that this phi of a, it should not be 0, which is the required condition. I hope you have understood this. Thanks for watching this video. Now, for the examples on this case of finding particular integral, please see next lecture. Thank you.